But V equals VO plus AT. V squared equals VO squared plus 2AX over delta X, which just means change of distance. Okay? X equals VO times T, 1/2 AT squared. Did these look familiar to you? You probably did them a long time ago at the beginning of the year. Okay? Yes?
Can we get that formula sheet on the exam?
Yes.
We're gonna,
For right now, you should be able to. I can't imagine you wouldn't.
I believe, my impression is you would have the formula sheet available to you because, for instance, you would have a formula sheet on the AP exam. They're not gonna hide the equations from you. What's more important is that you know how to apply those equations to different types of examples and situations. In addition to knowing these equations, you should know what each variable stands for. For instance, what do you think the V stands for? Velocity. So, if you don't already know, this would be a good thing to have. Velocity is meters per second. VO is also a velocity. What's different about VO? That's like the initial. The O really means original. So original, initial velocity, whichever. What does the A mean? Acceleration. And it's also the only thing that has the units of meters per second squared. What do you think the T means? And time is always measured in seconds. X, sometimes represented as a D, depending on which type of textbook you're using. Distance could be represented by D, oftentimes it's represented by X. The reason is because of the coordinate system. If you're looking for the displacement horizontally, that's like the X axis versus the Y axis. So you could also have X, meaning distance. All right? Now there's nothing you have to write down here because it's in front of you and there's space out to the side of each slide. In case you want to make any notes, you don't have to. I'm not collecting this or doing anything. Does anybody else need a handout? So I'm going to go through it kind of quick and then we're going to get to some examples. And so each day, what my intent is to go over examples and these topics that you would see on your exam. And the last half, you start working through the review that you have, and you can ask me questions so that you feel more comfortable about it. Okay? That way, by the time the exam gets here, hopefully you feel very confident. All right? So here we go. What does an acceleration mean? If something accelerates, what do you think that means? Change of speed in a direction. So you could change your velocity. Acceleration by definition is change of velocity. So you're either speeding up, slowing down, or changing direction. Right? Displacement. Displacement is from where you ended up minus where you started. Okay? There is a difference between speed and velocity. Velocity is the displacement over time. So by definition, acceleration is change velocity over time. From this idea, change velocity over change time. That triangle, delta, means change of something. Change of velocity would be like velocity minus VO. Guess what happens if you solve this for velocity? You add VO to the other side, you get V equals VO plus AT. This definition is the same thing as the first equation that you have right here. That's where it comes from. Okay. If you have something in kilometers per hour, and you've done dimensional analysis before, anytime you have something in kilometers per hour, you multiply by 1,000 to go to meters to get rid of kilometers, and you always get rid of hours to get seconds on the bottom, right? When you do that, you always end up doing the same steps. One of the problems you have in your review is converting 80 kilometers per hour. Let me show you the shortcut. If you're doing the same steps every time by multiplying by 1,000 divided by 3,600, just divide by 3.6. If you have kilometers per hour and you want to go to meters per second, that's a quicker way of doing it because you're doing the same steps anyway. What do you think you would do if you had meters per second and you wanted to go back to kilometers per hour? You'd multiply by 3.6. All right? Acceleration is a vector. Do you remember what it means to be a vector? What does a vector have that a scalar does not? Direction, right? When you did vectors, you probably, someone traveled this far north and this far west, how far are they from where they started? That kind of stuff. Having an angle. If you have a negative acceleration, what do you think that means for the object? What is it doing?
Slowing down.
Typically, it's slowing down or stopping. A deceleration means it's slowing down. Negative acceleration could be slowing down in the positive direction or speeding up in the negative direction. I'm just letting you know these things because the sign does make a difference. Because we're talking about linear acceleration, there's a positive direction, there's a negative direction. The negative just indicates the direction, that's all it does. All right, so here are the same equations that we're using. They're just written there again. So now we're going to do some examples. In any linear acceleration example, if you can find the three things that are given, you can solve for anything else. Okay? So for these examples, again, you don't need to write it down, but see if you can find three things that you know about each problem. We can make some room up here. For instance, in this first one, what is one thing that we know? All right, we know the initial velocity, right, is 23. The car is initially traveling 23 meters per second at the beginning of the problem. Are we going to make that V or VO? VO, that's our original or beginning velocity, right? So that's 23 meters per second. Well, what is 7 meters per second then? It's just V, or it's our final velocity. Finally, what else do we know? Time is 4 seconds. Again, if you can identify three things that you know, you can pick one of these linear equations and solve for what you don't. For instance, what is the acceleration? Which equation has these three givens and the acceleration in it? Is it going to be the first, second, or third equation? The first one will get you there in one step, right? So then you just plug in your value. And now you might be able to do this and skip some steps, and that's fine. But if you don't know where to start off by writing the things that you know. It comes out negative because it's slowing down or stopping. That's all the negative means, because we were going 23 meters per second, now we're going 7 meters per second. We slowed down. The acceleration was in the opposite direction of motion. Did I have another one on there, didn't I?
On the same slide.
Take just a couple minutes and see what you get for this answer. If you're not sure where to start, see what your three givens are. Starting from rest means what?
Starting from zero.
Our beginning velocity is 0, right? If something starts from rest or it's dropped, the initial velocity is 0. Goes down, that's a length or distance. And like I said, I don't know if you represent distance with a D or an X. On the AP exam, for instance, the equation sheet uses an X. Acceleration at 1.5. Acceleration at 1.5 meters per second squared means each second that goes by, the speed increases by 1.5. So after 2 seconds, it's now going 3 meters per second, then 4.5, 6, so on. Well here, which equation do we want to use if we want to find the velocity when it reaches the bottom. That's right, the second equation, right? So you're just matching up which equation has what you're given and what you're looking for. So if you're not sure how to solve a linear acceleration problem, write down your givens, you should have 3. Pick the equation that solves for what you need in one step. About 10? It's like 10, 10.1, right? I mean, you guys should check it, I could make that up, you know? Yeah. All right, I'm gonna skip this next one, because I think you already know how to do it, you can do it for practice, and if you have any questions, you can ask tomorrow. I wanna try some different types of problems. For instance, have you done problems before involving a graph, like a velocity versus time graph? Well, let's do one. That'll be fun. Something else that an AP exam would have, or another way of getting information, in addition to it being a word problem, you could see it graphically. It's really the same type of problem, just for instance, you could have a velocity on one axis, time on the other. If you have velocity versus time graph, it gives you the same information, but instead of it being a constant acceleration the whole time, it could change. Like for instance, how do you think you could find the acceleration going from 0 to 15 meters per second in 2 seconds? It would be 0 to 15 in 2 seconds, so what's your acceleration? 7.5, right? It's half. Another way of thinking of it, it's the slope. It's rise over run. You go up 15 meters per second divided by 2 seconds, the slope plus 7.5 meters per second squared. So it's just another way of getting information that if it's not in words, it could be by a graph. What do you think your acceleration is from 2 to 6 seconds? 0. Well, does that mean that you're stopped? No, it just means you're not changing your velocity. You're not speeding up or slowing down. Your velocity maintains a constant 15 meters per second. There's no acceleration, but you still have a positive velocity. What do you think is happening here from 6 to 8 seconds? A negative acceleration, which means this object is slowing down. It went from 15 back down to 10 meters per second. And then here, your greatest acceleration, if you go from 10 to 20 meters per second in 2 seconds, what do you think your acceleration here is? Yeah, 10 meters per second squared, right? 'Cause that's acceleration. So that's what's meant by a velocity versus time graph. Linear acceleration also includes objects that are falling. If an object is in the air, whether it's dropped, whether it's thrown straight down or thrown straight up or whatever, what do you know automatically? The acceleration is what? Negative 9.8 meters per second squared. Some books use positive, some use negative, more use negative because it's going down. So if you know that something is falling, the acceleration is due to gravity, 9.8 meters per second squared, where the negative just implies that it's going down. All right? So now you still have the same linear equations, but now you know your acceleration is gravity, which is negative 9.8. All right, so let's try this example. Again, I'm not going to go over every single slide. You have that in front of you. If you have questions, you can always ask me questions today, tomorrow, whenever. Just wanna do a little bit, because I know it's probably been a while, you probably did this at the beginning of the year, so. In identifying your three givens, if the rock is dropped, beginning velocity is 0, because you didn't give it an initial velocity. You didn't start off by throwing it. Okay? Drop from a bridge, 25 meters. So the distance down is 25 meters. How long does it take to reach the water below? If we know beginning velocity and the distance, what's our third given that I haven't written down yet? Gravity. We automatically know acceleration due to gravity, negative 9.8 meters per second squared. So now you can look at your linear equations and figure out which one will get you what you need to know. So if you want to first find out how long does it take to reach the water, which equation can we get there in one step? That would probably be, yeah, if we want to find the time first, you can do it in any order, it really doesn't make a difference. But if you want to find the time first, I'm going to use the third one, where I've got x equals VOT 1/2 AT squared, which is also a nice equation to use because when the beginning velocity is 0, this whole first term, anything times 0 goes away, right? So then we have x is 25 meters equals 1/2 times negative 9.8 t squared. Now, the 25 meters is technically down, so this should be negative. But let's say you forgot to do that. Will it really impact your final answer? Not in this case, because you can't take the square root of a negative number. You have to make it positive anyway, right? But anyway, 25 meters divided by 4.9 square root time square root of 5. 2.2. You guys want to check that? This is where I start making up stuff. 2.26, around 2.3 seconds. Do you all typically use significant digits? Sure. If you, if you're asking, then no. If you look at how many significant digits you have in the problem, if you just make sure your answer has the same number, that's the easiest way to do it. Okay. We have 25, that's 2 significant digits. 2.3 has 2. How fast is it going when it reaches the bottom? Now you have a couple different equations. Now that we know the time, we could use the first equation or the second equation. It doesn't make a difference, you should get the same answer. So v squared, VO squared, plus 2ax. Find the final velocity, beginning velocity is 0, 0 squared is still 0. 2 times acceleration, negative 9.8, times the distance down 25 meters. This will tell you the speed of the object right before it hits the water. Looks like about 22 meters per second. All right. How well are you all following what I'm doing? Does this make sense?
Yeah.
Okay. Because if it didn't make sense, please stop me or ask questions. All right. But that's essentially linear acceleration. You probably spent a couple weeks on it. We just kind of flew right through it. So if you have questions, just ask. Kinematics in 2 dimensions. Vectors, scalars, resultant. Let's try this example. Again, I'm kind of skipping over the notes, the concepts. If you want to go back and read those, if you don't remember what it is, you can always do that and ask me questions. I just want to get to the examples because from what I've heard from people is they want to see more applications of these equations. You don't really need to do any math here. You can do this in your head. Robert walks 1,500 meters down the road, stops, walks another 1,200 meters. You don't know which direction. But what's the maximum displacement Robert could be from where he started? At most, he could be 2,700 meters from where he started. What's the minimum he could be? 300. He could have walked 1,500 in one direction, 1,200 meters back towards his house. Your answer could technically be anything from 300 to 2,700 because Robert could have walked at an angle. Lewis drives 3 miles east, then 4 miles south. How far is he from where he started? If that's 3 miles, that's 4 miles, and this makes it right triangle, what do you think this side is going to be? 5. Have you ever heard of 3, 4, 5 triangle? Or, if it didn't work out really nicely and smoothly like that, Pythagorean theorem, I heard a couple people mention that. Pythagorean theorem, a squared plus b squared equals c squared, right? So, 3 squared plus 4 squared equals that resulting, that hypotenuse squared. So you've got 9, 16, that's 25 squared, 25 is 5. Either way. Okay, going to move on to past vectors. Projectiles. See how quickly I'm going over this stuff. I'm trying to give you time. Then that way, once you get all this and you come back with questions for me, you went too fast on that part. Could you do another example like that, and that'll be fine. A projectile means that the object is moving 2 dimensions at the same time. First thing that's important to know about projectiles, it can either be a horizontal launch, or it can be an angle launch where it goes up first or down first at some angle. So one has an angle, one doesn't. Those are the only 2 types of launch problems you could have. A horizontal launch would be throwing something horizontally, a ball rolls off the table, something like that. An angle launch implies that it's launched at some angle above the horizon. Did you guys do projectiles before? All right. Velocity in the x direction stays the same the whole time. Again, velocity in the x direction stays the same. So for instance, when that ball is rolling at 2 meters per second off the table, it keeps going at 2 meters per second horizontally, even until it hits the floor. The velocity that changes, however, is this velocity as it falls. As things fall, they do what? They accelerate due to gravity, they speed up. Every second that goes by, they're now moving 9.8 meters per second faster. So after 2 seconds, that's going 19.6. So that's why you get this parabolic path. For horizontal launch problems, the easy way to do horizontal launch problems, there's only 2 equations. So make some room here. Tennis balls hit horizontally, so that's how you know it's horizontal launch. First of all, it tells you it's hit horizontally, and also there's no angle given. The 2 equations, there's one equation that describes the motion horizontally, one that describes it vertically. Because things can move left and right or up and down at the same time, we're going to call the distance horizontally the x distance, the down distance is y. We don't want to call them both d for distance because that'll get confusing. To describe the motion horizontally, the equation we have is x equals vx times t. This just comes from the equation velocity equals distance over time. There is no acceleration horizontally, it maintains a constant speed. However, in the vertical direction, you initially have no speed because if it's thrown horizontally, there's no initial velocity vertically. If there's no initial velocity, this VOT would go away, and that distance down in the y direction would equal 1/2 times the acceleration, which is due to gravity, times t squared. If you have this equation and this equation, that's all you need to solve any horizontal launch problem. For example, this tennis ball is hit horizontally 16 meters per second. Well, it's hit horizontally 16 meters per second. The only thing that has velocity in it is right there, velocity in the x direction. From the ground, 1.25 meters. If it's 1.25 meters high, do you think that's the distance in the x or distance in the y direction? The y direction. Now, it doesn't look like you have very much in the way of givens, but we always know when something's in the air, gravity is 9.8 meters per second squared, and it's typically negative because it indicates the down direction. We could also make y, because it goes down 1.25 meters, negative as well. But even if you didn't, when you solve for time times a scalar, it's always got to be positive. Can't have something moving in a negative time. How long is the ball in the air? If you don't know the time, time has to be the first thing that you're solving for because it is in both equations. So using that second equation, y equals 1/2 gt squared. The downward distance, 1.25 meters, equals 1/2, gravity negative 9.8, t squared. You can find the time it takes to fall 1.25 meters. About 0.51 seconds. If you want to find out how far from the base, that is in the x direction, does the ball land? Well, it travels horizontally at a constant 16 meters per second for every second it's in the air. So if the ball's in the air for 1 second, it goes 16 meters per second. 2 seconds, it'd go 32. Well, it's only in the air for about half a second. So how far do you think it's going? About 8 meters.
What is Vx?
Vx is the horizontal velocity. The reason that x is there is because it tells you that it's going horizontally, not vertically. It has to be the velocity in the x direction.
Alright. So when you usually solving it, do you solve for the y-axis first, and then you solve for the x?
If you have the vertical height, yes, but there's another way you could be given the problem. You could actually know that, for instance, if I had said it lands 3 meters out, then you can use that to find the time. So if you're not given the time has to be the first thing that you solve for, but whether or not you use this equation or the x equation depends on what you're given. All right. So I'm going to stop there for today because I want to give you some time, the last 20 minutes, to start working on the review that you currently have, to give you time to ask questions while I'm here. Okay? So that's my plan each day, is to go over examples and review stuff about half the period, and then give you time to work on your review so that you have a chance to ask questions. All right, thanks.